All right, let's get started. So this is exam one. I guess we'll call it the go over because we do the review before the test and then we do the go over after. Problem number one, f of s, I'm gonna bring it up here, is equal to 4s plus 13 all over s cubed plus 6x squared plus 13s. And the problem was to find f of t. So this is one where you had to go back and find the time domain response of the system. And so how do you find the time domain response of the system? You have to go ahead and do partial fraction expansion to make it look like the tables, and then you can bring it back to the time domain. So we got to modify the signal so that it looks like the table. Well, the first thing we can do is we factor out an s, right? And we factor out a s because we know what one of the roots are, right? We have that the root is s equals 0, or one of the roots. The next thing we need to do is solve for the roots here. And let's do them by hand. Quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a, which is equal to negative 6 plus or minus the square root of negative 16 over 2. Negative 6, what's the square root of negative 16? What's the square root of 16? 4, but it's negative 16, so it's 4i all over 2, which is 3, negative 3, plus or minus ij, or I2, or 2j. So now, we talked about putting this in standard form. So it's s minus the real part plus the imaginary part squared, right? And then we can do partial fraction expansion because this looks like the table, right? So we can solve for a. A is going to be equal to 4s plus 13 over s plus 3, that quantity squared, plus 2 squared, evaluated at s equals 0. So we have 13 over 3 squared plus 2 squared. 3 squared is 9, plus 2 squared is 4. 13 over 13, which is equal to 1. B at an angle of theta is going to be equal to 4s plus 13 all over s, evaluated at the positive complex root, s equals minus 3 plus 2j. So that's going to be equal to negative 12 plus j8 plus 13 all over negative 3 plus 2j. You would probably need your calculator to do that because you've got complex numbers. So I'll use my calculator. And I ended up with 2.24 at an angle of minus 63.4. So now we can substitute that over here. I said equals, that should be plus. So that's 1 over s plus b at an angle of theta, we just calculated, 2.24 at an angle of minus 63.4. This multiplies s plus 3 squared plus 2 squared. And remember, if you look at your Laplace table, to be able to use the sine term, you have to have omega in the numerator. Omega is 2. So I need a 2 over here to be able to use the Laplace table. I just multiplied 2.24 by 2 by including that in the numerator. So I don't want to change the result. So if I multiply by 2.2, I have to divide by 2 and get my numbers that way. And so now my f of t is equal to 1 over S, which is equal to 1, plus 2.24 divided by 2, e to the minus 3t, because it's e to the whatever the negative part is, I mean the real part is, sine of the imaginary, the omega term, 2t, minus 63.4 volts. That's the way that I suggest you do it. Some people did it by doing AS plus B equals that, which is perfectly fine. As long as you showed your work. Like I saw a couple people in their test, magically they ended up with AS plus B, which means your calculator did it, not you. And I didn't give you full credit for that because you got to show your work, right? So you can't just go ahead and say, oh, it's these values. It's fine to do it that other way, but you need to show your work. Questions on number 1? We did that a lot last semester. We did it at the beginning of the class, right? We did a review where we did a bunch of problems. We did a complex root problem, just to get some additional practice. But again, it's important to see where this comes from because we're using Laplace extensively. Any question on number 1? Anybody in TV land have questions? Nothing? All right. Let's go to number 2, pole zero maps. Again, another review term. So we had an f of s equal s squared plus 2s all over s plus 4 times s squared plus 6s plus 34. Draw the pole zero map, right? Or find pole zero map. Okay. So we need to have the poles and the zeros. So we're going to take f of s and simplify it a little bit. We're going to factor out s out of the numerator. And out of the denominator, we don't know what the roots are, s squared plus 6s plus 34. So again, we just do the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac. So 4 times 34, 120, 136. All over 2a. You can see, and I'll do this a little faster, 36 minus 36 is minus 100. Take the square root of that, we end up with negative 10j, or sorry, 10j. So that's negative 3 plus or minus not negative 3. This is why did I say negative 3? It's 6, right? So it's negative 6 plus or minus the square root of 10, or plus or minus the square root of 100, negative 100, which is 10j, all over 2, which is negative 3 plus or minus 5j. Putting that here in our standard form, we have s plus 3 squared, s minus the real part, plus the imaginary part squared. Now this is all factored out. We know what the poles and zeros are. We know what the roots are. So we do the zeros are the roots of the numerator, 0 and minus 2. And the poles are minus 4. And then I've got complex conjugates here, right? I have negative 3 plus 5j. And negative 3 minus 5j. If you remember from when we've been talking the entire time, we said that the number of poles is always equal to the number of zeros when you include finite and infinite poles and zeros. So technically, you only have 2 zeros there. You have 1 more at s equals infinity. Right? Because you need 3 to balance out the 3 poles that you have. So now my pole zero map I have a 0 here, a 0 here. Those are my zeros, my finite zeros. Here's one of my poles at -5. And anytime you have a complex number, you have to have complex conjugate pairs. So I would show those two. And then if you really wanted to be complete, you would say S equals infinity. So we'll call it S for 0 to show that it has its actual 0 at S equals infinity. So you can't really draw that on a pole 0 map. You kind of just identify that that has the additional one if you want to draw it on a pole 0 map. Questions on that one? Yes, sir.
So let's say if you're missing either a pole or a 0, it's kind of safe to assume that S is going to equal something within the same one.
Yeah, so if you have a pole, right? If you have one extra pole, then you need a 0 at S equals infinity. The other case, it doesn't exist in the real world, but if it did, you had more zeros and poles, and technically you could have a pole at S equals infinity, but they don't exist. I've never seen them that way. Okay. All right. Any questions on number 2? I was hoping that was going to be a really quick and dirty problem, right? Just do a little factoring, but not a particularly tough problem, I was hoping. Again, we're going to use, and it's good to reintroduce pole 0 maps because we really need to keep, discussing those, because as we start to see when we do what are called root locus is essentially an almost unlimited number of pole 0 maps. And what I mean by that is you show poles and zeros, multiple poles and zeros on a pole 0 map or on a map, but you have, an infinite number of points. So keeping track of the pole 0 map is a really good thing because we need it in the future. That's why I keep harping on the fact that we have a 0 at S approaches infinity, because that becomes really important. All right. Transfer function time. Did this one look familiar at all? We basically did that first part, right? In class, we did that first one. And then the second stage, whoops, I forgot the resistor. It's just a really simple voltage divider network with no capacitors. So a really simple gain one. So this is R3 and this is R4. So I immediately turn this into Z1 and Z2. And then I call this output over here, I'll call it V out 1. This is V in. V out 1 is also equal to V in 1, right? Because they're the same point. And then this is V out. So V out 1, which is the output gain, over V in is going to be equal to negative RF over RI, negative Z2 over Z1. Over here, it's the same process. V out over V in 1, which again is the same point as V out 1, is equal to negative R4 over R3. I didn't even bother talking about Z's because there's nothing to really combine there. So then I multiplied those together, V out 1 over V in, multiplied by V out over V in 1, which again, these two are the same, is going to be equal to V out over V in, right? So that's going to be equal to positive, because the two negatives cancel, Z2 over Z1, R4 over R3. If you would have gotten it to something to look like this, because remember we talked about this in the review, I'm not expecting you to do a lot of math. You would have gotten 90% of the credit if you would have gotten it this far. Why? Because it's just a simplification, right? To get that final 10 points, you needed to go ahead and substitute in, but really to get most of the points, I was hoping to see this. Was this a hard one to get to? John would say it should be easy by now, right? Because you guys did this a lot. In 342 or 241, I don't know which class he covers op amps in, but I know he does them extensively, so. And we've done a bunch in this class as well as the previous class, so hopefully. It's not too bad. Do you want to see the full Monty substitution for Z2 and Z1 and see all the math? It's not too bad. We see that Z2 is going to be equal to R2 in parallel with 1 over C2S, right? So that's going to be product over sum. R2 over C2S all over R2 plus 1 over C2S. We common denominator the numerator and invert and multiply. That's what we get, right? I didn't show the common denominator stuff. We did that a bunch. If anybody wants to see it, let me know. But that's the process for doing the common denominator. Z1 is really easy. It's just the sum of the two, right? R1 plus 1 over C1S, which is equal to R1 C1S plus 1 over C1S. Now you can substitute into here, R2 over R2 C2S plus 1, all over R1 C1S plus 1 over C1S times R4 over R3. We have fractions and fractions, so we invert and multiply. We have R2 times C1S times R4 all over R2 C2S plus 1 multiply by R1 C1S plus 1. Multiply that by R3. And then if you really wanted to expand it out, I mean, you foil it, but I don't know if foiling it here really provides any value at this point. To me, I prefer to see it like this, but you're certainly welcome to foil it. But at the very least, you don't have any Z terms in here. So this is all the way down to the base, you know, equation, essentially. Questions on this one? I was very generous on doing this because there was a lot of, y'all made things very complicated for no reason.
You usually do.
Yeah, I will acknowledge what you said. I'm not necessarily agreeing, but this really was not that complicated. That's what my intention was. Is there anything here that made it more complicated? Did I make this look too easy, or? It's not my intention.
You didn't make it.
I didn't make it look too easy, so it's still challenging?
No, I just,
Okay,
like, literally in my notes, I started it with disease and then just went in completely different direction. I made it hard.
okay. What's that, Aaron? That's okay. There's more than one way to skin a cat. I know one person actually tried to use the current approach, which is fine. And that's like the base, you know, approach to do it. You just model these as impedances, right? This is Z1 of S and Z2 of S. And the difficult part about doing it in the time domain, right, is you have integrals and derivatives that you have to deal with. It makes it very difficult to do that. Over here, I just treat them as constants.
One thing I got caught up on was like knowing the rules of operating, there has to be 0 volts here and here, so I wasn't sure I was like, these currents gonna flow at all. But
Yeah, no
it has to be something.
Current's gonna flow here, but there's no current in here. So it flows up over into here and down over here and over and down. So the current goes to the load. Doesn't go into the op amp, it goes to the load.
That is also what I
use the current. It's okay. But the thing is, that's a derivation that I don't expect you to be able to do. It's not a hard derivation, but it's a derivation nonetheless, where you have to prove what the inverting, the gain of an inverting op amp is, right? You have to do that. And I basically said, we don't have to prove that. We've already done that. So just use the fact of an inverting op amp. But even if you use the current, you still would have had to use I, because the voltage, the current through the sum of these, right? This is very difficult to find this current I, because one, you've got a voltage drop across the resistor. The other one is the integral, right? It's the amount of charge that's stored. So that becomes very difficult. Actually, you have to write a differential equation to do that. That's why we don't do that unless we absolutely have to. Okay. One or two people put J omega in stuff. This is not AC circuit analysis, right? So we can't talk about J omega because that only applies for AC systems. This works for any frequency, any voltage. Doesn't have to be AC, it can be DC, it can be exponential, whatever it needs to be. All right. Any questions on number 3? Fair, not fair? So the thing too is to reflect, wow, I made it much harder, and I'm not picking on anybody. I made it much harder than it needed to be. So the question is, did you understand that material, or did you kind of get it and maybe a little, perhaps a little more studying or practice would have actually helped you? Oh my God, it's just 2 inverting op amps. That's all it is. That's really what it is.
But another question for this example.
Okay, sure. Well, one of the things too, and this is just something because I'm almost 55, and as I've gone through the career, what you find is the more skilled you get, the engineering problems are just as complicated, but they seem easier to you. They just make more sense. So when you first start working, or when you're in college and you're trying to look at this stuff, it's like, oh my God, this is really complicated. But at the end of the semester, the hope is, oh, the stuff we did at the beginning of the semester actually is pretty simple, because you've learned, you understand. So our job, all of us collectively, right, is to help make the stuff easier for you to process, so that when you get out and work, you get that same thing. I remember the first time I did my real quote unquote job, somebody's asking me to do something. I was like, oh my God, I'm stupid. I can't figure this out. I have no idea what's going on. But then I realized I'm not stupid, and I can figure this out. And so you start chunking away, you start working at it, you start thinking about it, you start making notes, you do what you need to do. And then you might ask a question or two. Can you provide some guidance? I'm not exactly sure what this means. And I'm so old, I started working in 1992. The internet ain't what it is today. So it sounds like, oh, I had to walk 5 miles backwards, it's up a hill, the snow to go to school. It's not that. It's just like the internet has made it so much easier for you to access information. You can actually do searches, and so hopefully that's part of your learning, which is YouTube's got a lot of stuff, because sometimes it's a different approach. It can explain things. They use different figures. You can certainly use that. Just be mindful though, that YouTube is not always right. Sometimes they do things and it can be confusing. So it's almost like YouTube should have a disclaimer associated with it. I guess what I'm saying is, don't perform open heart surgery by watching a YouTube video. Okay.
I changed my timing though.
Hey, I do it all the time. I kind of am a backyard mechanic, or I even have I like to putter as an engineer. I just like to do that. And so my heating system, sometimes it's acting wonky, and it's like, I'll do some researching. Oh, it could be this, it could be that. And so I'll start troubleshooting. And I've never had to have a heating person come out to my house because, the thing doesn't work. I could figure out how to make it work. And I'm not suggesting I'm a master plumber by any stretch, but the little things that I'm trying to do, I can do a lot of those things. Oh, the pipe is leaking. I need to either go and crimp it, or I got to solder something. How do you solder? And you just kind of work through the process, and then you watch it enough times and you get skilled at it. So yeah, YouTube is really good for that. All right, enough yapping on number 3. How about number 4? This was the easiest problem. by far. I think. So I said, find the transfer function x of s over r of s, right? X of s is the output, r of s is the input. So the very first thing you can do, oh, these are all in time domain. I have to take them to the Laplace domain because I'm looking for a Laplace domain transfer function. So this is s cubed, x of s, plus 6s squared, x of s, plus 11s, x of s, plus 6x of s equals 6r of s plus 6s times r of s. Factor. On the left-hand side, I'm going to factor x of s, s cubed, 6s squared. On the right-hand side, I'm going to factor r. Now I'm looking for x of s over r of s, which is going to be equal to that's it. All you needed to do for this problem. Questions on this one? Fair, not fair? Do you feel like this was the easiest problem on the test too? What's that? Yeah, I made it worth 20 points, right? So that's pretty good. Number 5. Might have been the most difficult, except if you remember what we talked about in class. I said, draw your free body diagrams and your dampers, springs, your inertias, all those things are going to oppose the applied force. So I draw my free body diagram. I have F applied in this direction. I have the K1 force in that direction. The force is associated with the movement, the position of how much that spring is in this case being elongated. So that's times x, because x is our position as shown on the figure. We also have a damper, and that is x prime, right? Because it's velocity. The damper is based on only if it's being accelerated or if it's velocity. We also have the mass times acceleration, because you got to store energy in that moving mass. And then the last one is K2, but K2 is on the other side of the mass. All that means is now, if I'm pulling the mass this way, the spring is being compressed. So K2 is in the same direction as the other forces. It's always opposing its movement. So now I take these to the Laplace domain. K1 times x of s plus b s x of s plus m s squared x of s plus K2 x of s is equal to f of s. Factor out on the left-hand side my x of s. So that's ms squared plus bs plus K1 plus K2 equals f of s. My transfer function, x of s over f of s, because it's output over input, is equal to 1 over ms squared plus bs plus K1 plus K2. Some people tried to say, oh, these two forces are going to be a K effective, which is going to be equal to K1, K2 over K1 plus K2. That's not the case. These two springs are not in series with each other. When two springs are in series, think about it. One spring is being compressed, right? And the other spring is pushing this way because it's being compressed, which means the other spring is going to fight it. So those are like resistors in parallel. I mean, they're in parallel if the two are actually in series. So if you have this, they're actually fighting against each other. They're not adding like resistors do. But since these were on two completely different points, two different blocks, there's no K effective there. They just add like they're in series. Because they're both opposing the movement of the mass. They are not restricting each other. So that's why you can't do a K effective here. Question on number 5. Yes, sir.
So instead you can't do K effective. Or just like your equation, your FFT, so you just call it K equivalent and go and it's plus or K1 plus.
You can, but with K equivalent, right? You're essentially saying I either have this configuration or this configuration, right? These are both impacting that same mass, but the mass resets everything. What happens over here has nothing to do. That spring is not opposing that other spring from being compressed or elongated. It's opposing the mass from moving in one direction or the other. So it's not really a K equivalent. They're two completely separate springs. Sure, Leo.
So K2 is opposing the mass, why is it not? Why is
It is. It's in the opposite direction. See right there?
No, why is it like?
Because they're both opposing. Both springs are opposing because the mass is in equilibrium. It's in a 0 point. It's not moving. So both springs are sitting there happy. They're in their equilibrium point. The damper is not moving. Everything is happy. Now all of a sudden we have a force. We're trying to move that mass to the right. The spring that was in equilibrium before now is being compressed. I don't want to be compressed. So I'm going to push back on the movement in that direction. The other spring on the other side says, hey, you're stretching me out. You're elongating me. I don't want to be elongated. I want to stay in that nominal position. So I'm going to have another opposing force. So these always try to oppose the motion. And the reason being is because if I let that force go, what happens? That block eventually will slide and stop moving when the two springs have reached their equilibrium point. If one spring is compressed slightly and the other one is elongated, they're both going to go that way, right? At some point, they're going to reach a point where they cancel each other out. It's only when you apply an external force. Now they're saying, hey, I don't want to be in that direction. So now I'm going to start to fight change. That's why they're not opposite each other. Number 6. I gave you a transfer function. I tried to be good about this. I didn't give you an f of s. I gave you a g of s. And I said, find the steady state output for a unit step input. So if my g of s is y of s over x of s, my x of s has to be a unit step, which is 1 over s, right? So y of s is going to be equal to g of s times x of s, which is equal to 2 over s squared plus 2s plus 8. Multiply that by 1 over s. Now I have to go ahead and take it to the time domain, right? That's going to be equal to a over s plus, now I got to do quadratic equation. So my quadratic equation, negative b plus or minus the square root of b squared minus 4ac all over 2a. The square root of negative 28 is 6 and change, or not 6 and change, 5 and change. So let's negative 1 plus or minus, let's just call it 5. Just make it easy. It's 5 point something, but we'll call it 5. So this is b at an angle of theta over s minus or s plus 1 squared plus 5 and change squared. In my Laplace table, this becomes e to the minus t sine of 5t plus theta, right? Right? If I look at the table, Just this expression over here is gonna be something that looks of that form. But the problem was, I wanted the steady state output. Steady state output means all the transients have decayed, which means this term goes to 0. I don't even need to solve for b at an angle of theta. I only solve for a. So a is going to be equal to 2 over s squared plus 2s plus 8, evaluated at s equals 0, which is equal to 2 over 8, or a quarter. So the only thing that exists in steady state is 1/4. Don't want to do that? No problem. So y of s is equal to 2 over s squared plus 2s plus 8 times s, right? That's what we got over here. Remember the final value fits theorem? Y steady state is equal to s times y of s as s approaches 0. So it's s times y of s, the limit function as s approaches 0. That's going to be equal to the limit as s approaches 0, s times 2 over s squared plus 2s plus 8, all times s. These cancel out. Limit function as s approaches 0 means anytime you see an s go to 0 equals the same result. More than one way to skin a cat, right? So if you didn't feel comfortable doing final value theorem, this approach works really well, right? Doing partial fraction expansion. And the good thing is you get the same result. If you didn't get the same result, that wouldn't be a good thing, would it? Oops. But you get the same result, so that's what we want. The last problem, people really struggled with it. Yes, sir.
You said since there's no decay before.
Yeah, because in steady state, right, all the transients decay away. So anytime you see an e to the minus something t, that term goes away. And so that's why I didn't even need to calculate b at an angle theta, because I knew that that term after 5 time constants is gone. So in steady state, that doesn't exist. The only one that exists is the unit step. That's why I just had to solve for a.
I kind of just guess. That one, on how to do it.
Trying to tell me you want me to take points off? Is that what you're suggesting? Because you didn't.
No, I'm pretty sure I did it correctly. I used the last thing on my new card that I had to use with the final value here.
Yeah, as long as you did it right, you should have got a quarter.
Yeah, I didn't get it, so I just wanted to see how you get from the actual equation to where you're at. So it's like, you're like, oh, this is the last one.
Yeah. I would have done this approach here because it's the most efficient. But I was showing you the other one because some people still aren't 100% comfortable with final value theorem. I hope you get comfortable, because when we look at steady state errors, you need to use that a lot. But like I said, you can still do this one by doing partial fraction expansion of the material we did last semester. You could get there from here. And that's the test. Questions or comments? Fair test, unfair test? Easy, hard, in the middle?
It's pretty.
No gotchas, no tricks, no. Chris is doing the side eye, so does that mean yes?
No.
No.
I'm not good stuff. There's just little things that kind of snowball over.
Okay. I think the average was an 87. Yeah. So like I said, I didn't grade the op amp one too difficult, because again, that's a lot of math, or maybe as perceived as doing a lot of math. So I didn't, if you did some work, if I could see that you were on the right track using inverting op amps, I probably gave you all the credit or full credit. Even if your answer was way off, because again, that's algebra. This is not an algebra class. This is a circuits class that does Laplace. But when you get out of industry, what you'd find is you would be expected to get it right. So the expectations we have here are different because we're just trying to get you to learn the material. And then obviously, if you have an unlimited time or perceived unlimited time, you're going to go back and check your work multiple times and make sure it makes sense and yada, yada, yada. Kind of go from there. But this is still good stuff. I remember when I was applying for a job, I had to do op amp stuff. And I had to derive it. They were looking for me. This is a company, they don't exist anymore because they made the fancy machines that made people here probably don't even know what a CD is. They made machines that would make CDs. And you guys know what CDs are?
Yeah.
Okay. Well, CDs have been gone for 20 years, right?
I don't think.
What's that?
I don't think new cars will.
I was gonna say, I think I have a 2012, doesn't have a CD player. That's 13 years, right? So normally when they start taking them out of cars, that's usually a sign that it's gone technology. So I just assume nobody has been buying CDs for 20 years.
I still.
You do? Oh. I just thought everybody just downloaded. They had iTunes or whatever. They just downloaded the stuff from the web. You could just buy the songs you want instead of buying the albums. I thought the only people who bought albums would buy vinyl. Because you get the nice big portraits and all that stuff. Like, I think you can go to Walmart. I don't even think they sell CDs. Maybe they do.
Yeah, they got like some use. I got
Oh, wow. Okay. I mean, I know DVDs have been around a long time, and I thought DVDs replaced CDs, but I don't know.
That's for my drug.
You have cassettes? You can still buy those? Wow. I thought those.
Yeah.
Well, the only reason why I think vinyl, well, there's two reasons. Supposedly it's better quality, but you get this really big space to do the artwork. And so when you used to have to buy records, the artists who are producing music would spend a lot of time in trying to make the covers and make it more interesting and add a lot of really interesting tidbits to it to make it, hey, I want to buy the album because it's a piece of art. Whereas if it's on a CD this big, you want to spend that much time that's that small, you can't really see it, it became less and less. Cassettes really destroyed that because with the cassette, right, it's really small. But now with vinyl coming back, you get really good artwork. And like I said, I thought everybody was streaming stuff. I didn't know people still bought CDs. Like your phone, when you listen to music, most people listen to the music on their phone, right? You don't have a CD player on your phone last time I checked. So when was the last time you actually listened to a CD? Am I right here? You don't put your headphones on and listen to a podcast or?
Sometimes I do. I got rid of Spotify. Like algorithm for killing music sucks. I was just doing the same songs. And like, you know what?
Well, make a playlist on YouTube. If you log into YouTube, you can have your own playlist.
Yeah. You can find anything you want.
Listen to me. I am hip. Telling you how to get it done. I'm kidding. But anyway, yeah. So that's some of the things, right? As your job stuff changes, you still need to be op amps. You still need to be able to do those things because it's a basic understanding. Circuit analysis. You never know when they're going to be that job where somebody's going to say, here's op amp, show me how to do it. Because it's such an easy problem that most people can figure it out on the fly as long as they make a couple of assumptions. And that's, again, the way that they can tell if you're, a reasonably competent engineer or not. I also remember when I took the PE, this was many, many years ago, they tried to make this really complicated op amp problem. And all they had in the feedback path was like this non-linear device. And so you just had to figure out where you were operating. It was such an easy problem, but they've made it like so extremely complicated by having this non-linear device. It was like, but I just need to pick a point like you would at any other time. And you just pick the point. So easy peasy stuff. But again, I took my PE in 1997. So I don't know if they still do that type of stuff. I'm getting old, or I already am old. So last thing, any other questions before I say my last words? But I apologize again for not making the test. I tried to get back as quickly as possible. We didn't leave until after 4, which is not a pleasant experience. Taking care of your dad in a wheelchair for 3 hours at a place that isn't really equipped for that. So I do appreciate everybody, being understanding. But my plan is, unless other stuff happened, is to always be there for the tests. Mark was there and he said, and I gave him all kinds of material. He was ready, so he could answer questions. He said it should be no problem. And I also gave him my cell. So if he needed to, he could call me and I could help. And I had a copy of the test with me, so I was ready to go. I tried logging in during the test while I was sitting there in the waiting room, but I couldn't get in. They didn't have Wi-Fi that was fast enough. It just kept handshaking or something, so it kept kicking me out. I actually was outside USM, so I had got there early enough. I went to get lunch. There's a Hannaford right there. And I went and parked and had a little bit of lunch on the USM campus, and it's the same or wireless system, so you can get it there as well. And so I was able to check email and do that. But I think his appointment was at 1, so I had to leave by 12:30. So I couldn't jump on. So, but yeah, I started driving back, and Mark said the test was done. I got a notification on my phone, so I was like, well, I guess I better get up early. So I got here at 4 this morning to grade the tests. So I've been here for a long time. It was very cold this.
Yeah.
It was cold and dark. For what it's like.
That sounds like me.
But I try to get the tests. I know you guys like to have the test results ASAP, so.
Thank you.
Yeah. Well, it works really well because my family, like I said, I'm here, they're in Florida and living the life, so. I called my family this morning and she said it was 75 degrees. And so it's like, please don't tell me that anymore. I'm getting more and more jealous. I tell them I'm going to leave in March, and then they're like, no, you can't go unless you take us with you. It's like, you didn't take me with you, so how does that work? All right, I'll stop babbling unless you really want to hear boring life stories, so. Anything else? Well, we had a test, so I'll give you the break of the day. Have a wonderful weekend. Enjoy it. I haven't posted a homework yet because we don't have new material to cover, right? So we have to get into the new material. They canceled our class on Tuesday, so that kind of, or sorry, Thursday, so messed things up. That's the policy. Take care, everyone.
Thank you, Paul. You too.
Take care.
Bye, Paul.
See you.
Feel like that was the first time.